mechanical support, you get equations of the same kind with the sound speed replacing the light speed. So that actually makes things even worse. So if you have a mechanical structure supporting the mirrors, in fact, you get an even stronger inequality. Gm over c squared is greater than ratio of light to sound velocity times the separation. So that's even worse. So that the conclusion is still true. So you can prove that there is no possible gravitational wave detector of that kind which will detect single gravitons. Well, let's go on then to the a more hopeful kind of gravitational wave detector, which is the single atom. That's just the gravitoelectric effect. Now we're looking at a single atom. Gravitational wave comes in. Another particle, either an electron or a neutron or anything else, is kicked out. Well, you can calculate then by quantum mechanics the rate at which this will happen. So here's the calculation. So you're looking at a quadrupole wave. The gravitational wave is a quadrupole. So the matrix element for, this is equation 11, is the matrix element for transition of the electron from state A to state B. So psi A is the wave function of the initial state. Psi B is the wave function of the final state. And x and y are just the two coordinates of the electron at right angles to each other. So that's a particular quadrupole with polarization at 45 degrees to the x and y axes. It doesn't matter. You could take the other polarization. It would give the same result. Then the cross-section for the kicking out the electron is given by equation 12, which is this standard formula from quantum mechanics for a quadrupole radiation process. So you have a lot of numbers in front. G is the coupling constant of gravitation, which comes out of the Einstein equation. Again, omega is the wavelength, c is velocity of light. D is this matrix element, and then you have a delta function for energy conservation. It says the graviton energy, h omega, is equal to the difference between the two state energies. So that's the cross-section. Well, that's, of course, a complicated thing to calculate. Doesn't look very promising, but you can make a very strong argument by writing down an exact sum rule. A sum rule in quantum mechanics is a wonderful device for getting simple consequences from complicated equations. You just sum over all the frequencies and everything comes out very simple. So this quantity S of A is the logarithmic average of the cross-section, averaged over energy, but with the divided by d omega over omega. So it's averaged over the logarithm of the energy. So it's the logarithmic average of the cross-section. And that you can calculate very beautifully from this formula. If you integrate over omega, and the delta function disappears, and you get just then products of matrix elements, which become matrix products. And in fact, you get a double commutator of this quadrupole with the Hamiltonian. And so everything becomes simple. And in the result is S of A, the logarithmic average cross-section, turns out to be just this quantity 14. And that's an exact sum rule. It's a very, very simple but powerful equation. And this This capital Q is then a property only of the initial state. The sum over the final states has disappeared. That just gives you a matrix product. So you get just the expectation in the initial state of this differential quantity. And the amazing thing is that all the constants have disappeared, that the mass has disappeared, the potential has disappeared, so the charge of the nucleus has disappeared. It no longer depends on anything except just the shape of the wave function and nothing else. So this Q is a pure number. And if you take the simple case where you're talking about a spherical wave function, that's just an ordinary bound state of an electron in an atom, which you'd expect to be the one which would react most strongly to gravitation, that then everything becomes absurdly simple. And you can then prove just by simple algebra that this capital Q, this coefficient here, is at least 3/4. So it's a number of the order of 1, which is at least 3/4. And if you take a simple model for the wave function, which is so typical of a strongly bound particle, like a ground state of an atom or a ground state of a nucleus, so r minus n, where n is some positive power times an exponential, that's a typical wave function for a bound particle. Then Q is 1 minus n over 6. So it's very close to 1. So that this Q, in fact, is just a number which is for ordinary atoms and nuclei close to 1. And the final result of this whole discussion is then that the logarithmic average of the cross-section, equation 14, is just equal to the Planck length squared, and that's all it is. Well, the Planck length squared is a very, very small area of the order of 10 to minus 65 square meters. So there's nothing you can do to change that. It doesn't matter what kind of an atom you're using or whether you're talking about nuclear forces or electromagnetic forces. The best you can do is a cross-section 10 to minus 65 square meters. So if you consider sort of to be, I can't any longer prove a theorem. I can't say this measurement fails for reasons, sort of for fundamental physical reasons. I say it fails just for practical reasons, that if you're looking at so anything that's even conceivably practical, if you had a gravitational source, well, let me just talk about gravitational thermal generators. That's an interesting subject in itself, and I won't spend long on it. That was worked out by Steven Weinberg a long time ago. How much gravitational radiation is actually being produced in the sun? The sun is a wonderful source of gravitational gravitons with observable energy. If you take a collision in the core of the sun, where the average energy of the particles is of the order of 10 kilovolts or so, then so you have mostly electrons and protons colliding together all the time, very hard. They will be generating gravitons, and that's about the best source of gravitons that you can imagine. It's producing huge numbers of gravitons all the time, and they all get out. They all escape from the sun because the sun is transparent to its own gravitons. So in fact, that's by far the best source of gravitons you can imagine. And that turns out to be 79 megawatts for the sun. Of course, it's a large amount of energy by human standards, but very small by astronomical standards. And So it turns out 4 times 10 to the minus 4 gravitons per centimeter squared per second. And if you multiply that by the cross-section, and imagine the whole Earth is used as your gravitational wave detector, then during the entire lifetime of the sun, you should, on the average, detect 4 gravitons. So it's just barely possible. Anyhow, that's not very encouraging. You can imagine better sources than the sun. You could imagine moving around the universe looking for better sources of gravitons. So there are things like hot neutron stars, which are much more actively radiating than the sun. They have very much higher average thermal energy. So they radiate maybe 10 to the 10 times more strongly than the sun, but they don't live so long. The total amount of energy in the form of gravitons is not all that much greater. The amount available is roughly the same, whether it's the sun or a neutron star. In the case of the neutron star, it comes out faster, but you don't gain all that much. And of course, you can imagine a detector which is bigger than the Earth, maybe closer to the source. So in principle, maybe you could do somewhat better, but not very much. And so that at the most you get perhaps 10 to the 10 gravitons could be detected during the lifetime of the source. And then there comes the argument about backgrounds, that any source of gravitons of that magnitude producing gravitons of the kilovolt range also produces neutrinos. And the neutrino background turns out to be enormously larger than the gravitational flux. The neutrinos have, of course, enormously stronger interaction than gravitons by something like 20 powers of 10. And so they're emitted in much more copiously. And also the detection probabilities for neutrinos are also much larger. So you get something like 30 powers of 10 favoring neutrinos against gravitons. So any conceivable graviton detector looking for thermal gravitons has to deal with this overwhelming background of neutrinos. So from a practical point of view, that seems to make the thing pretty hopeless. But it's not the same, it's not so satisfactory a conclusion as you had for the LIGO. Well, the final set of detectors, which I'll talk about very briefly, are the coherent detectors, that's non-thermal detectors, which are then the thing that Gerstenstein proposed 40 years ago. That comes from this process of coherent conversion of gravitons into photons. So here are the equations governing that. This is the coupling, this first equation, 24, is just the coupling of the gravitational field amplitude, which is Hij, which is the Einstein tensor, multiplied by the electromagnetic energy tensor. So capital Tij is the electromagnetic energy tensor. And that is then a combination of a classical magnetic field, capital B, and the quantum magnetic field, little b. And so you get a mixing of classical and quantum magnetic fields. So the interaction finally gives you a bilinear term, linear in gravitation and also linear in photon field, multiplied by the classical background field. So now you imagine your detector consists of a long magnet with a strong classical magnetic field, and you put in photons at one end and out come gravitons at the other end, or vice versa. And the beauty of that is that since the process is coherent, the probability of conversion goes as the square of the length. So the probability of conversion is actually this equation 29. It says probability of conversion is b squared, the square of the magnetic field, times d squared, which is the length of your magnet, divided by this fourth power of the velocity of light. It's always the velocity of light which kills you. So the probabilities are amazingly small. And again, this is a purely classical effect. Planck's constant has disappeared. It's a classical mixing of gravity with photons. And the conversion length, capital L, is 10 to the 25 centimeters, which is of the order of a kiloparsec in astronomical units, 10 to the 25 centimeters, divided by the magnetic field in Gauss. So it means for any conceivable magnet, the probabilities are very small. But still, again, it looks as though in principle it might perhaps be feasible. But then there comes a fatal flaw into this argument too, that nonlinear electrodynamics. It turns out that the Maxwell field, after all, is not linear. And this was, in fact, the discovery of Euler and Heisenberg already in 1936. It's one of the most beautiful things that Heisenberg did when he was still a scientist. And they worked, and he and his student Euler worked out the theory of the polarization of the vacuum produced by pair creation, that is, electrons and positrons popping up and down in the vacuum, produce this fourth order term in the Maxwell equations. So the Maxwell equations are inherently nonlinear when you allow the Maxwell field to interact with electrons and positrons. So this is the Euler-Heisenberg nonlinear electrodynamics, which tells you that, in fact, the speed of light in a classical magnetic field is less than it would be in a vacuum. And so this final equation 35, it's the amount that the speed of light is reduced in a magnetic field. So B is the classical magnetic field. HC is the critical field, which is 5 times 13 Gauss, 10 to the 13 Gauss, which is actually about what you get astronomically in a pulsar. A pulsar is a magnetized neutron star, which typically have fields which are just about equal to the critical field. So this, in a pulsar, these numbers can be quite large. The Maxwell field really becomes strongly nonlinear. And that tells you then this coherent conversion doesn't work. That if you have graviton and a photon going at different speeds, they're not going to be coherent with one another. So the coherent conversion simply fails. And so that happens then to be true in a neutron star. And also, if you imagine a detector in which your magnetic field is more of a reasonable terrestrial magnetic field of the order of 10 Tesla or something of the kind that was used. By the way, the people at CERN actually used this as a device for detecting axions. There was an experiment done at CERN looking for the coherent conversion of photons into axions, axion being a hypothetical particle with mass zero, which might exist and be detectable in this way. And so they did the experiment and also got a null result, because they were not looking for gravitons. But if you took an experiment of that kind with an unreasonably long magnet of the order of, say, 100 million kilometers or something of that kind, still, it turns out that the coherent conversion doesn't work. The nonlinearity of the Maxwell equation is enough to defeat you. So it seems that this kind of detector also doesn't seem to work. Anyway, I'll leave the subject there. I don't want to get drowned in details. But so the final conclusion is that the possibilities remain open, that quantum gravity may be in fact correct, as everybody, all the experts believe, or it may be correct but with confinement, so that gravitons are always confined and not visible. Or it may be that gravitons don't exist. So we can't yet decide that. But I think it's an interesting subject, and certainly there's a possibility of pushing these arguments very much further. Thank you. So I'll be happy during the meetings if the experts like to come and talk. We can discuss it in detail. Thank you.
Any questions, comments?
Yes.
It clearly is very difficult to probe the distance or energy scale where quantum effects of gravity become important and measurable, as you have illustrated beautifully. But the one place where I can imagine two scenarios I wonder whether you might have thought of. One is in a hypothetical world, which is consistent with everything else we know, in which there existed very heavy monopoles, which we've been looking for. We haven't found them, but they might still exist. And our present understanding of quantum field theory, the standard model, would allow such monopoles to exist without truly understanding gravity, say at 1/10 of the Planck mass or 100th of the Planck mass. Given such monopoles, one could imagine accelerating them in a magnetic field, say, confined by electric fields, and constructing a monopole, anti-monopole annihilation detection, which you would do very carefully. Once a month, take two such monopole, anti-monopole pairs, colliding them at what would be close to Planck energy, center of mass collisions. In which case, the quantum effects, according to standard semi-classical quantum mechanics, would be enormous.
No, I've not thought about that. Well, I hope you will.
That, of course, presumes the existence of monopoles that we could mine someday. Second possibility, of course, is the more likely one in the properties of black holes themselves, which, in a sense, are highly quantum mechanical, as Hawking already argued. The quantum mechanical effects are significant, albeit for the black holes we have observed, very teeny once again. But it's still a matter of, as you know, of current highly intense theoretical analysis of the quantum mechanics of black hole horizons. It is not beyond, it is quite possible that black holes whose non-blackness, whose radiation and eventual collapse, eventual disappearance, is quantum mechanical, will manifest effects when we are able to study the horizons of even large black holes that that open a window to the quantum mechanical effects of gravity directly, and that maybe not in the kinds of photoelectric or tests that you were, but and what is happening there is that you're using the enormous blue shift provided by that background geometry to enhance what are probes that we can, the radiation that we see, which back towards the horizon is blue shifted to Planckian energies. And again, people are now arguing, in effect, what are the conceivable, visible, and dramatic effects at the quantum horizon of a black hole. Those are two places where, who knows, conceivably one might sometime in the future directly observe quantum effects of black holes, of gravity.
Good. Well, I hope you'll pursue that. I should say I looked a little bit at the second one, but I don't pretend to follow all the literature. The interesting part of the black hole theory, of course, is the final disintegration when the black hole disappears in a puff of gamma rays. And the problem there, so in that case, the graviton effects will be large. And in principle, you could observe gravitons there. But you have grave difficulties just because the final disappearance of the black hole is attended with a fireball. And the fireball conceals everything in the last microsecond. It makes it very hard to do the measurement. So I didn't go into details, but certainly there's a lot of interesting questions to explore. I hope you and your people will do it. Thank you.